Our example is now going to be a beam, a simple beam. We have one element. On the left end, we have a wall, and we also have a roller at point B. And what you're asked to do is solve for the rotation at the roller, and E and I are constant. So we're going to do a second order beam equation, and then we will also do a fourth order beam equation. And so as we start here, we're going to need to make some observations about our beam. And so at the left end of the beam, we have three kinematic restraints. The wall has full translational restraint and also rotational restraint. Over at point B, we have one translational restraint in the vertical direction. So let's go ahead and draw a free body diagram. Down here, we've got our beam with the point load 50 kips. We've got a total of 15 feet on our beam. I have a reaction force. I'm going to call that F1 from the roller at B. Over all the way at the left end, we have full translational restraint, which is provided by two perpendicular forces. And we also have a moment. So you see we have four unknowns. We have only three equations of equilibrium. And so this is a 1 degree indeterminate beam in the transverse direction. Something else to point out here as we get into our example is the moment equation, which we're going to need in our second order beam equation, is going to have two pieces to it. There's going to be one value for m of x from a to b, and a different value or function m of x from b to c. So the segment that we're going to be interested in is over here from a to b. We're going to work from the wall to the roller. So let's go ahead and draw a free body diagram of a cut beam. So what we're going to do is cut this beam over here at a distance x. So we're going to set up our x coordinate system over there at the left hand side. All right, we've called this the blue saw at x. So literally the distance to that cut is going to be a distance x. And so we end up with a free body diagram from doing that, which is going to have two pieces to it. I've only drawn the piece on the right. And so I've got a segment that has a length right in there of 10 minus x. We also have 5 feet from F1 over to the 50 kip load. And so that's what we want. That is going to be the internal moment, and that's going to be between A to B only. So I'm just going to highlight this here. This is for values of x from 0 to 10 feet only. We're going to end up with something different beyond that. So how are we going to find m of x? The best way to do it is I'm just going to sum a moment right at the cut. That's the most efficient way to go solve for the orange m. And so doing that, I end up with an equation that has m of x in it. We've got our 50 kip load multiplied by 15 minus x, its lever arm, and then also F1 times its lever arm of 10 minus x. So we've just got a little bit of math to do here. And if we do that, we end up with a very nice equation for m of x. And I'm just going to reshuffle that just slightly here. And such that I've got all of the x's in one spot. And then that is just a big constant right there. And again, you notice that we have an unknown in this equation. We have F1. And so that's something we're going to be able to solve for. I'd also notice that the units that are present here are going to be kip feet. And that's what's about on our beam from our load, and also our dimensions are in feet. So we've got a second order beam equation that we are going to solve, and we've got some boundary conditions. So let's go slide back up here and take a look at that picture all the way at the very top.